The topic we want to cover today are some of the special rules for finding the interior and exterior angles and then one angle of polygons. Now, so far what we have done is we've dealt with angles and parallel lines, angles that have special relationships, and angles within a triangle. So today we're going to deal with angles and polygons. Okay? A polygon is a closed plane meaning two-dimensional, figure whose sides are segments that intersect only at their endpoints. Okay? It's easier to see than some of our very typical polygons, triangles, squares, trapezoids, etc. What are not polygons is something like the following, because the figure in blue intersects somewhere other than at the endpoints, or the following, because they're not line segments, but they have curves to them. A regular polygon is a polygon with equal side lengths and equal angle measures. Two very typical examples: a square, all angles are 90 degrees, all four sides are equal, and an equilateral triangle. All angles are 60 degrees, all sides are equal in length. Now, the rule for the interior angles of a polygon are very straightforward. The words may sound a little bit confusing, but once we go through some examples, you'll get the idea. The interior angle sum of a polygon, the rule is the sum of the interior angles of a polygon is 180 degrees times 2 less than the number of sides. So put into a formula format, the sum of those angles, S, is equal to 180 times n minus 2, where n equals the number of sides. Now, the following chart should hopefully make it clear as to how this rule works. Okay? So, we're going to start at our baseline of triangles. And what we're going to do is we're going to identify the polygon, the number of sides, what the figure looks like, the number of triangles we can form from the figure, and the measure of interior angles. So a triangle, which has 3 sides, is obviously only one triangle, and as we've already discussed, is comprised of 180 degrees. Now, a quadrilateral, which has 4 sides, if I were to draw a line from one vertex to its opposite or opposite vertices, so for example from D to B, you'll see that I formed 2 triangles, and 2 triangles total 360 degrees. Now, I could have gone also from A to C. It's just whatever you choose to do. Okay? I just can't cross the 2 of them. Now, a pentagon, which has 5 sides, well, if I'm going to start at this top vertex here, I draw to the 2 opposite vertices, and you'll see I formed 3 triangles, which is another 180 degrees. Okay? Again, I could have done, oops, don't lift the pen and erase at the same time. I could have gone from this vertice, or vertex, to those 2 opposite it. It doesn't matter. I still have 1, 2, 3 triangles. And then finally, for a hexagon which has 6 sides, I'm going to be able to form 1, 2, 3, 4 different triangles, which brings me up to 720 degrees. What you will notice throughout this is that the number of triangles formed is 2 less than the number of sides of the figure. And that's why the formula works the way it works. Okay, so let's go through a couple of examples. First example, I have an, an octagon, and I want to know the sum of the interior angles. Octagon is 8 sides. 8 minus 2 is 180 times 180, which is 6 times 180, which is 1,080 degrees. It's as straightforward as that. If I have 8 sides, I can form 6 different triangles. Now, the figure here, I'm going to count out that I have 9 sides, nonagon, so that I'm going to be able to form 7 distinct triangles. And in total, it's going to come up to 1,260 degrees. So again, the first two, I'm finding the sum of the interior angles. Now, the third example is going to be a little different. I want the measure of one angle of a regular decagon. Well, to find one, I need to know what they are in total. Decagon, deca for decade, is 10 sides. So I know that in total, I'm going to have 1,440 degrees. But I want one angle. So to figure out one angle, and since it's a regular decagon, that means all 10 angles are going to be equal in length, or measure, I'm sorry, then each one is 144 degrees. Okay? Now let's go to the last topic we're going to cover, which is the exterior angles of a polygon. If you look at the diagrams below, in the green triangle, I have 3 exterior angles. When I add those 3 up, they come to 360 degrees. In my quadrilateral or square, I have 4 exterior angles of 90 each. They come to 360 degrees when added together. And then finally, in my pentagon, I have 5 angles of 72 degrees. That comes to 360 when I add the 5 of them up. So, hopefully you've been able to now see that the rule is, in a polygon, the sum of the measures of the exterior angles is 360 degrees. That is it. It does not matter what type of polygon it is. Okay? It could be regular, non-regular. It's still going to be 360 in total. Now, you have to read these questions carefully. Find the measure of an external angle. That means one of a regular hexagon. Well, what do all of the exterior angles total? 360 degrees. So whether it's a hexagon, a quadrilateral, a pentagon, an octagon, a decagon, it's still going to be 360. But why do I need to know it's a hexagon or a regular hexagon? Because I'm going to deal with 6 angles that are equal in measure. And the 6 are going to be 60. The 6 of them will be 60 degrees each. All right. The last example. What is the measure of angle 1 below? Well, if you were listening to the rule, 130 and 130 are 2 of my external angles, and they total 260 degrees. The 3 of them together have to total 360. That means angle 1 is 100 degrees. Now, that's the most direct way to get there. You could have gotten there another way. If this angle is 130, the angle adjacent to it is 50, since they form a straight line. This angle is 50, since they form a straight line. That angle has to be 80, because 50 plus 50 plus 80 is my 180. Well, if this angle is 80, then 1 has to be 100 because it forms a straight line. That's a little bit a roundabout way to get there, but will work. So remember the rules for the sum of the interior angles and the sum of the exterior angles of polygons.